Good day and welcome everyone to the second webinar in the International Society for Respiratory Protection series on response to the COVID outbreak. This webinar is featuring the Americas response to SARS-CoV-2. I have a note that there's a lot of echo. Is anyone else hearing that? It is not on my end. Okay, so no, there is not a problem on my end. All right, sorry, I will continue then. The next slide, please. So if I can, first of all, let all of you know the agenda. So we will start with some introductions, tell you a little bit about the ISRP if you're not already familiar with us. And then we will address the two webinar topics and we'll have a Q&A session. The Q&A session will actually be at the end of each of the talks. So there'll be one after the first talk and one after the second talk. And the planned timing is half an hour with 10 minutes for questions for each presentation. Next slide. So first of all, let me introduce myself. I'm Eva Dixon. I'm the president of the International Society for Respiratory Protection, and I'm moderating this webinar today on behalf of the Americas section. And also in the background, we have Michael Parham, who is our past president and web person extraordinaire, and he is assisting me with moderating and running this webinar today, and thank you very much to him. Today's speakers, you can see up on the screen, we have two sets of speakers. Our first set of three speakers are from the National Research Council of Canada, and they are speaking to particle filtration efficiency measurement of personal protective equipment for Canada, which was the urgent response to the COVID-19 pandemic requirements for respiratory protection as it was conducted at the National Research Council of Canada. And then our second speaker is Dr. Margaret Sietsma, who is an assistant professor of environmental and occupational health sciences at the University of Illinois, Chicago. And she will be speaking about respirator program considerations for non-healthcare workplaces, evaluating the need and implementation guidance for COVID-19. And Margaret's been very active in various discussions and recommendations around the use of respiratory protection for COVID. Okay, next slide, please. So just a little bit about ISRP, if you are not familiar with it. The organization was founded in 1983. It is a nonprofit organization whose charter is to provide an educational and informational service to all individuals involved in respiratory protection. Our purpose is to bring together the occupational health and safety professionals in the field of respiratory protection. Everyone is welcome to join. We consist of user groups, industrial hygienists, manufacturers, regulators, anyone who has a professional interest in respiratory protection. And our membership is open, and on the webpage, www.isrp.com, you can learn more. You can consider joining. We have sections by region, so each of the sections has information also posted up on the website. So when you join, you actually join a regional section, as well as the International Society. And of course, the efforts of the ISRP are to work on various endeavors that will encourage health and safety, exchange of knowledge and information, promoting research, and effective use of various devices, both domestically for some of our members and in the developing world for other applications. Next slide. I would also like to point out to you that we have another scheduled webinar upcoming on the 3rd of December, which is being hosted by our European section that focuses on the European response to COVID-19 outbreak and discusses many features of the European response, including latest information on what can be used in Europe with some case studies and lessons learned. Next slide. So the registration for that webinar, presumably you already found the registration page as you registered for this one, but it is on the ISRP website. So just a reminder, administratively, the webinar is 90 minutes long. Speakers have 30 minutes with 10 minutes immediately afterwards for questions. Please use the Q&A feature to pose questions to the speakers, and those questions will be moderated and asked of the speakers by myself at the end of their session. Don't use the chat for questions. You can use it for information that you want to send to others or to the moderators specifically. And then the webinar itself will be posted with a private link on YouTube to all registrants, and the presentations will also be available on the members only part of the ISRP website. Next slide. All right, and just a general thank you to all of our members who have supported this webinar series and everything that the ISRP does. All right, thank you. So Michael, if you can let go and the NRC team can take over. So NRC, all right, and Richard is sharing. So over to you, Richard.
Thanks very much. I appreciate the opportunity to have the talk here today. I'm having a little bit of issues with the not having access to the mute button on my system, but I think if I hold down the space bar, it'll work. So yeah, I'm going to talk to you today with my colleagues, Joel Corbin and Triantafillos, Koukoulas, about the NRC response to COVID. And this was really an urgent response to develop the capability to test mostly respirators for their particle filtration efficiency. And this was work in collaboration with the Public Health Agency of Canada, particularly Joe Tonelli. So we began in the very early stages, is about March 30th, we began the COVID response at NRC. And at that time, the Canadian regulator, which is Health Canada, for approving respirators and for sale of respirators and the use of respirators in Canada, only recognized NIOSH as the sole certification. There was no domestic manufacturing of N95. And as far as we know, no domestic capacity for testing for PFE against the NIOSH standard or the ASTM standard, which is used for surgical masks. The orders that the government of Canada placed in response to COVID was over 100 million respirators, and some of them were starting to be delivered within a few weeks. Now, the government had a difficult time finding respirators, as you can imagine, that had already certification. So they were getting respirators from all across the world, from China, from Korea, from Europe as well. And any of the ones that could come in and be delivered was what we were purchasing. These were divided into various risk categories. So there would be risk level 1, which would be already approved respirators coming into Canada that we really didn't have to test because it would meet the normal standards that we follow, the NIOSH standards. But then there was another risk category, which would be respirators from manufacturers that had some quality control and some demonstration of certification. And then the risk level 3, which was the highest risk. And this governed most of the respirators that Canada was receiving. These had no history from the manufacturer, very little quality assurance data, no certification that we knew of. So that was NRC's goal, was to develop the capability to reduce that risk. And the testing to do that, or the most important testing to determine the quality of these respirators, are the particle filtration efficiency measurements. And this is just a quick slide on what that is. And the test is simply we generate an aerosol of specific mean diameter and a characteristic standard distribution about that mean diameter. Those particles are carried in an aerosol or carried in a medium air to a set of photo detectors, and we measure the concentration of the particles upstream from the respirator or the filter we're measuring, as well as downstream from the respirator. And of course, the ratio between the two is related to the filtration efficiency. At the same time, we also measure the pressure drop across the respirator, which is relevant for the breathability of the respirator and how comfortable these are to wear. So in the very early stages, I think it was a Monday when we began, we got a quote for the TSI 8130A, which is the necessary piece of equipment to test against the requirements of 42 CFR Part 84 and the standard procedure, which is this NIOSH TEB APT STP 0059. And so this TSI 8130A, you can see this instrument in blue, is a necessary piece of equipment for that. That measures the mass-based filtration efficiency of filters. We ordered that, but at the time, we weren't sure whether it would be delivered in a timely manner. We weren't sure if the borders, there's going to be export restrictions. I don't know if you recall very early on that the US was beginning to limit exports of N95 from the US, and we didn't know whether or not that would be extended to this equipment as well. And so to mitigate some of that risk, we thought about building a system in-house ourselves. Now, we're all metrologists who were involved in this project, or at least mostly metrologists involved in this project. And so our experience and our expertise is in the measurement science. And we do have one area within our metrology research center, which has studied black carbon aerosols for quite a long time. So particulate coming from jet engines or turbines or things like this. And so we had some experience and we had some equipment already. And so I brought a diagram to one of my colleagues in the black carbon metrology team, Greg Smallwood, and I asked him, so how long do you think it would take to build up something like this? And he said, oh, I think it'll take about 3 days. And it turns out that he did it in 5 days, and the team did it in 5 days. And I think the only reason why it took 5 days is because we said, okay, we can build it, but we all have to make sure that every component has a calibration certificate, is in calibration. We have quality system documents written up to demonstrate our capability and to assure our quality. So this is a typical of what we do in metrology, where we have a test capability and we also have a quality system associated with it. And so you can see in the bottom right here, this is our home-built system. It's not an efficiently turnkey system, but we have quite a few people running it. But it actually turns out to be a very powerful system. And you can see a little closer to schematic here. We generate the aerosol in this area here, and then we measure the concentration both upstream from the mask and below stream from the mask. But we also have particle size resolution, so we can measure the concentrations as a function of particle size as well. And so in the top right here, you have sort of what the output plot gives us, which is this is the size concentration distribution of particles upstream, and the red curve is the downstream distribution, and the blue curve is the filtration efficiency. And so we built this, but we also needed to validate to ensure that it would work. And so one of the experiments we did a series of experiments looking at the repeatability, the reproducibility, but also the sensitivity. And one of those experiments right here in the middle was just taking an N95 mask and compromising it, so poking holes in it. And we could clearly demonstrate the difference between a 95% effective mask and something lower than that. And this here demonstrates the change in filtration efficiency for every 10 holes, you get about a 5% reduction in filtration efficiency. So just to give you an idea of the timeline and the people involved, this sort of became an industrial scale set of testing. because we had plane loads coming in. They needed to be tested so that we could ensure decision making as quickly as possible so they could be released to the frontline healthcare workers. So we started in March. We ordered, we had the quote on March 30th. We ordered on April 1st, I believe, which is probably the fastest procurement in government history as far as I know, so maybe under 2 days. Then we designed and built the system in a few days, and we had the full validation completed by April 17th. And we had an exchange of letters with PHAC between NRC, which indicated that we would do the testing on their behalf and they would make decisions based on our results. And we provided the quality system and all the documentation, the validation for that to be accepted. It turns out that the requirements also for massive scale testing, it turns out that logistics was a difficult problem because planes would come in, we didn't know when they would come in, we didn't necessarily know what would be on the planes, and we didn't know when the mask would arrive. So we had someone here, Harold Parks, involved in the logistics, and Triantafillos, who we'll talk to today, was in charge of the buildup of the TSI 8130As when they arrived and implementing those and testing on those. And Joel Corbin will give the next talk, was working on the home-built system, which we call the FEM system, and he did a lot of the analysis and supporting the buildup of that capability as well, and he has a great talk coming up after me. But this testing also involved over 80 NRC staff when we were at full thrust. This involves people in the testing, people in logistics, people building components for us that we needed, people producing salt solutions that we needed. And another milestone here later on was the development of the F2299 procedure for testing surgical masks. So this is a completely other standard that we adapted our FEM system to be able to accommodate. So that system could also measure salt aerosols as well as latex spheres according to the ASTM standard. So how this kind of looked from the industrial scale, from the immediate response, the plane would arrive, we would get some notification, PHAC would send people to Hamilton, Measurement Canada would sample the respirators as they would come off the plane. They would be sent to PHAC for pre-inspection. Those would then be sub-sampled and brought to us. And so when we received the mask, we would receive about 50 masks per lot, and we would test about 14 of those. And I'll describe what we had to do that. And so normally these tests would take, if you met the NIOSH testing procedure, would take about 2 hours. We had to do that much more quickly, and so we had to provide some deviations for that. But the way this typically looked is we would have 14 samples. We would mount those samples on a plate in order to get them into the testing apparatus. But we would do a pre-test, sort of where we would test 3 from that lot, and if they all met above 85%, we would proceed to the full testing. But if any one of those failed, we would reject them. And that was just because in the very early stages, we were getting a lot of product was very, very poor. I don't know if you've read any of the articles about that, but it was a little bit like the Wild West, where people were stealing N95 on the tarmac or redirecting them to other countries because they were such in high demand. So this is some of the deviations that we had to come up with in order to test very quickly, but also test very safely, and also to accommodate the wide variety of quality that we were getting in the very early stages. So some of the respirators were being made from material that's not normally used for respirators, and for which I think the NIOSH standard wasn't particularly designed to address. But the NIOSH standard normally accounts for 20 samples per lot, or 20 samples for the certification. All of the samples are to be conditioned, and now conditioning is just keeping the samples in for about 25 hours, or 25 hours plus or minus 1, in a chamber of high humidity, 85%, and 38 degrees, which is supposed to represent the human body, so somebody wearing them. We reduced this to 7 samples that were going to be tested conditioned, as well as 7 samples tested unconditioned. We wanted both, and I'll tell you why we did both conditioned and unconditioned samples. Now, if we wanted to test for the full 200 milligram loading that's normally required for N95, that takes about 2 hours per sample, and we would just not have the bandwidth to satisfy that. That being said, the work that we were doing was strictly for the response to COVID, and so wouldn't be used in industrial settings. And the 200 milligrams is for respirators that to be used in things like cement grinding or salt or mining or things like this, where there'd be sort of low visibility environments, high particulate environments. But for hospital settings or frontline healthcare workers or residential settings, that kind of loading wouldn't be expected. And so we have decided to do about 7.5 milligrams of loading, which resulted in about testing about 10 masks an hour instead of 1 mask every 2 hours. So the reasoning that we calculated would be okay to do the 7.5 milligrams of loading was that we looked at the worst case scenario of indoor air quality that we could find in Canada, which turned out to be on a particular spike during monitoring on the Toronto subway platform. And we took that spike, the concentration of that spike, and we used the average volume that somebody would breathe in on a 12-hour period. And from that, we calculated that in the worst case scenario, you could have to filter 3.3 milligrams in 12 hours of use. And so the 7.5 milligrams we were testing to would represent about 3 8-hour shifts. And in the hospital setting, the air is even much cleaner. And you'd expect about 7.5 milligram hours would represent about a 32 8-hour shifts. And so that could also accommodate reprocessed respirators. So if they were worn, reprocessed or sterilized and reworn again, it could still be accommodated. It would still be covered by our testing. So this is what our conditioning chamber looked like. And this is one of the deviations that we had investigated, whether we really needed to do this conditioning. Because in principle, we could test a lot more quickly and deliver results a lot more quickly if we removed this 1 day of testing required by the standard. So we did investigations fairly early on where we did conditioned and unconditioned and investigated whether there was actually an impact. And typically about 98 or 99% of the time, there was no impact. But in some cases, there was impact. And the assumption that conditioning, which is supposed to represent somebody breathing through it and humidifying the mask and compromising the electrostatic charge of the respirator, the assumption is that that would compromise the mask and make it worse. It turns out that for one lot here, you can see that unconditioned, you would get about a 60% filtration efficiency. But if you did condition it, you'd reach the 95% filtration efficiency. That's clear that if you put the respirator on unconditioned, which is what we would do, what the healthcare worker would do, you would have much less protection over the first when it was first put on. And so we did some measurements also to see how quickly that filtration efficiency would be built up in this case. And it turns out even at 4 hours, it didn't really increase much above 65%. So releasing lots of potentially 1 million masks that were no good for the first 4 hours or 24 hours of wearing it was really something we needed to make sure didn't happen. And so we accommodated that in the standard test procedures to make sure that we did both and we could identify whether there was a difference between them. And of course, there are masks that do show degradation in performance when you do condition them, and we monitor that as well. So it's important to both do conditioned and unconditioned. And so in the end, what we've done so far over the past 8 months is we tested about 4,350 samples. That represents about 860 lots. We've been working with Canadian manufacturers, both in the material development phase. So there's now Canadian manufacturers producing melt-blown material to be used in respirators and surgical masks. We've helped quite a few dozen or more Canadian manufacturers in developing the capability to produce respirators as well. We're also working to transfer our knowledge to other test labs where we're giving them all of our procedures, our designs, our know-how about how to do the work. And we're also supporting sort of proficiency testing so that they can demonstrate competence to regulators. And so the first lab has come up a few weeks ago, has received their accreditation for performing the PFE test or for NIOSH for respirators. It's Vancouver Coastal Health, but there's other people, IRSST, there's other labs coming up, CSA, who are building up the capability as well. And we're engaged with all of them. So I'll pass now along to my colleague, Joel Corbin, who will discuss in more detail the development of the PFE measurements for surgical masks and more details about that. Thanks very much.
Thank you, Richard. So I'm going to talk a bit about the basics of respiratory particle filtration, and then go into some details on two test methods, the NIOSH test method, which is what we're mainly talking about today, but also the ASTM test method, which is used for medical masks. So before we start talking about filtration, we need to understand what aerosol particles we're talking about. When I say aerosol particle here, some people call it bioaerosol. Bio just means it comes from a biological source. What you see here is on the right axis, the volume, the total volume of particles at a given size, which is given on the x-axis. And you can see that the largest volume of particles comes from the mouth. These would be extremely large particles, which would be visible to your naked eye. And then smaller number of particles comes from your lungs and larynx when you're talking or breathing or coughing, with coughing being the most important. And we need to think about these sizes in terms of how they behave in the environment. So first of all, these particles are going to dry, losing a lot of their volume and become a lot smaller. Second of all, if we're talking about these particles carrying disease, we need to think about, do they get into the lungs? So shown at the top here is the lung deposition efficiency of these particles, which shows that the largest particles are captured with the highest efficiency. But this curve is a little confusing because those large particles will be captured in your upper airways, whereas the smaller particles will get deeper into your lungs. And so they remain quite dangerous. We don't know much about how this applies to COVID, but it has been shown for some diseases that getting deeper into your lungs is worse. You may want to think about this plot in terms of bacteria. So the bacteria are normally about 1 micron in size. So even the small particles on this plot are quite large in a biological sense. And now if you look at the other two curves, we need to not only think about lung deposition, but how well do these masks work? So if you have an N95, which is designed to have minimal penetration, an excellent seal around the face, especially compared to other, to casual face masks, that N95 will have a maximum penetration of about 1%, meaning that about 1% of particles can actually get through the mask. So there's no point trying to do better than that with our mask. And at the same time, we also have leakage around the N95, which is about 1% as well for small particles, but remains much higher than the penetration for very large particles. And now for a cloth mask, that will be much higher. So that can get up to 30 or 50% for a cotton mask. So with that context, now we try to filter the particles using a fiber filter. The fiber filter will have two different categories by which it can capture these particles. The first is mechanical capture, where the particles, due to their inertia or diffusion, come into contact with the fiber and then stick to it. So by diffusion, the smaller particles are captured, and by inertia or interception, the larger particles are captured. And then the second category is electrostatic capture. And this on the right is a little bit more complex, and it's used in technologies such as N95 masks. So if I plot those different mechanisms, this plot's a little bit complicated, but all I want you to see here is that the capture efficiency of a mask is the smallest at around 0.1 to 0.3 nanometers in diameter. And that corresponds to that region of interest that you saw earlier. So this is the reason that we do our tests at this size, because this is the most challenging condition, and we want to make sure that these respirators are going to work. Larger particles are normally captured relatively efficiently. So now I'm going to focus on the two test methods by ASTM and NIOSH, as I mentioned. The differences are shown here in color. So the ASTM method uses polystyrene latex spheres. This just means that it's a particle of a known size and known density. And we try to have that at a single size of 100 nanometers. We then pass those through the mask at a known velocity and count before and after how many particles we have. For the NIOSH test method, we use sodium chloride particles of a slightly different size, but due to their higher density, it works out to be about the same. We pass those through the mask at a fixed velocity, and then we count the total mass before and after the mask. So one method is counting the number, one method is counting the mass. So when I said that we use 100 nanometer particles, this is actually not that easy to do. What we do is we put these particles into an aqueous solution and we spray the particles into the air, and then we dry and count the particles. So when we spray the solution into the air, we have droplets, and hopefully those droplets contain one PSL particle. Then you get what you want, a singlet. If they contain nothing, you'll just see a residue. If they contain more than one PSL particle, you'll see multiplets. And all of those things which are not singlets create artifacts in our measurements. So if you have a detector which can see all of these sizes, we'll measure too high because of both residues and multiplets. And if we can only see large particles, we might not even see the singlets, but only see multiplets. And this would bias our final measured efficiency of the mask. So what we've done at NRC is two things. First, we switched from standard PSL to something called CML, which is the same thing. It's just that we don't have surfactant, and that reduces the residues. So going from here to here, the residues are significantly lower. And second, we use a relatively expensive research grade instrument to classify the particles by size before we count all of them. And that lets us produce the graphs that you're looking at, which Richard also introduced. And that lets us say that we're only going to take results for the 100 nanometer size of interest. Something similar is done when we use NaCl. Now, to switch dimensions completely, we can also think about the charge on these particles. When we spray them, particles generate a lot of charge. You might have heard about the Kelvin bucket experiment, where you just generate charge by creating a spray. But this charge has an influence on the electrostatic effects that I mentioned earlier. So either if the material is charged, it will attract the charged particles, or if the material is not charged, it can still be induced to have a charge by the charged particle. And you see that on the data on the right. So the dark bar shows the output of our spray, which is highly charged, so therefore highly filtered. The next bar shows after we've treated this to neutralization, which means it reaches charge equilibrium. And we have a much lower efficiency because we've removed the electrostatic capture. The other three bars illustrate this in more detail by showing +1, -1, and 0 charges. And you can see that +-1 doesn't really make a difference because this is an induced charge effect. And 0 charges has a much lower efficiency, meaning that that improvement was due to the charge on the respirator. And now another completely different dimension is the phase velocity, which is to say, how fast is the aerosol, or how fast are the particles being pushed through the mask? In the real world, this corresponds to how hard are you breathing, and also how large is the respirator that you're wearing. So in the NIOSH test method, we use a challenging high phase velocity of 25 centimeters per second, whereas in the ASTM test method, we're actually allowed to use anything that you see here on the x-axis. And if you compare that to the response on the y-axis, you see that that results in a big change in the filtration efficiencies that we can get for these for these two example masks. So the important thing here is that if you choose to test under relaxed conditions in the real world, you may actually not have as good an efficiency as you expected. And I just want to note that the highest limit here is not representative of coughs, but of kind of normal breathing. In normal breathing, you can even locally exceed these speeds, but the mask itself should dampen that effect to some degree. And then again, in the real world, we have to think about this in the context of leaks in the respirator. If you're leaking 10%, there's no point worrying about 5% here. And finally, this is for, these data here are for medical masks and not N95 respirators, and not for homemade reusable masks. With that, I'll pass on to Triantafillos, who will continue the next section of the talk.
I hope everyone can hear me now. I seem to have a bit of an issue with my microphone. Okay, just a moment. Right, so we will now move to the third part of the presentation, where we will look at some of the measurements we performed at NRC for particle filtration efficiency from a metrological perspective. influence factors, and some knowledge that we gained throughout the testing. So let's go a step back and revisit what do we mean by the TSI. When we refer to the TSI, we talk about the TSI 8138, which is an automated filter tester. And this is what is required by NIOSH for the tests. Now, this is quite a simple device, very noisy. It produces 76 decibels of pure noise. So it really isn't very comfortable for the operators to work for 8 continuous hours. But in a very nutshell, what it has photo detectors in the upstream and the downstream. And the ratio between these two provides you with the particle filtration efficiency. Also, it has a pressure transducer, which allows you to measure what is the resistance of the respirator. So these two are very important metrics. The particle filtration efficiency tells you how effective the respirator is in terms of blocking particles of specific size. Resistance effectively is a measure of the breathability of the mask, how easy it is to breathe through it. Now, the FEM systems, as Joel and Richard explained, is a far more sophisticated system. It was actually built at NRC. And I think here we should point out the two differences between the TSI 8138 and the FEM systems. The fact is that the TSI only measures mass-based filtration efficiency, particle filtration efficiency, whereas the FEM systems produces the number-based particle filtration efficiency and the mass-based particle filtration efficiency. So of course now this is something that people tend to overlook, and this is something that we often talk to our clients when we discuss about the results between different testings on similar respirators between different laboratories. Sometimes you get a deviation within the results. And you have to take a step back and think, okay, now what is the issue? If we're using similar methodologies, why do we tend to see different results? And on the left-hand side, we have produced a simple table that is divided into 2 sections effectively. What happens if we actually vary the geometric mean diameter, which is specified by NIOSH, 75 mean plus or minus 20 nanometers, with a fixed standard deviation of 1.82. And then what happens if we actually fix the diameter at 75 and we vary the deviation? So effectively, this column and this column, NBFE, which stands for number-based filtration efficiency, and mass-based filtration efficiency, give you an idea of what the impacts of different particle size distributions and deviations have on the efficiency. And you can actually see that the measurement that really has the highest impact upon is the mass-based filtration efficiency. So it deviates by quite a large margin compared to the number-based filtration efficiency. And of course, that relates to the reported values of the efficiency. Why do they change that much? Why do they deviate? And as an example, I'll show you the blue curve, effectively, which is represents the results of the FEM systems that they acquired using the so-called green line media paper. This green line media paper is, by the way, a reference artifact produced by the TSI 8138, and it is being used on a daily basis as some sort of calibration of the equipment to make sure that we're seeing the right particle sizing. So the blue curve tells you what is the filtration efficiency as a function of the mobility diameter of the particles within your charging aerosol. Now, the green curves effectively show you what happens if you have a particle size distribution that varies in terms of the mean. So if you compare the 3 green curves against the blue curve, you will see that depending on how big or how small your particle sizes are, that will have an impact on the filtration efficiency. So for example, as you can see, the larger the particles are, the higher the filtration efficiency is. So effectively, this is what sheds light into this argument. This is why we get different results between different facilities. It really depends on the properties of the challenging aerosol. And now we talked about the fact that both systems have differences in terms of what kind of measurements they yield. The TSI-8130A yields the mass-based number filtration efficiency. The FEMS systems, which is the NRC custom-made system, gives you number and mass-based filtration efficiencies. Now, and these are the two graphs that show you the relationship, if you like, or the correlation between number-based versus mass-based filtration efficiency, which is the left-hand side. And as you can see, the deviation seems to increase as the percentage of the mass reduces. Now, on the right-hand side, you see that the converted mass-based filtration efficiency of the FEM system compares and correlates pretty well to the mass-based filtration efficiency reported by the TSI. So we know now, we have some data, a wealth of data, as a matter of fact, that actually show you that, yes, the system that is being required by the NIOSH standard, the TSI-8130A, agrees pretty well with the custom-made NRC system, the FEM system.
Triantafillos, can I remind you that you've only got a minute or so more?
Yes.
Okay.
All right, sorry. So let's keep very quickly and talk about the fact that sometimes we need to validate assumptions. So when it comes to validating a specific protocol, for example, the NIOSH procedure that says that we need 75 nanometer aerosol particles, you need to validate that, yes, this assumption is correct. And this is what we did at NRC. We validated that assumption using both systems into one. And we found out that actually the geometric mean diameter of our TSI is 56 nanometer with a deviation of 1.78, which is well within the requirements of the standards. Of course, we needed to verify and validate that, yes, all our equipment agree with each other and the repeatability and reproducibility is adequate. And these plots show you exactly this, that we have a linear performance within both our equipment. Of course, you need to validate yourself, not against within NRC, but also between external collaborators. And this is just a graph that shows you how well the agreement exists between NRC and external laboratories. From this, of course, this kind of historical data, this wealth of historical data, you can start understanding the uncertainties of the system. And one such result is that really uncertainty scales with repeatability and the particle filtration efficiency. Mounting, of course, has a big impact. So as you know, there are many different kinds of respirators and masks, and all of them have unique characteristics, which makes it mounting a little bit of tricky. And also gluing, depending on how well you glue and at what points of the respirator, has an impact on the resistance and the filtration values. So for example, the gray part of the tables show you what the values are when you glue along the entire perforated perimeter. The white cells shows you what happens when you glue just along the bottom part of the respirator. So how you glue and how you mount also has an impact. Finally, we can quickly talk about NIOSH standard, whether such an existing standard is adequate for the COVID framework. And the requirements of the standard at NIOSH is that you have to really test your respirators over 200 milligrams of loading test. But our results have actually shown that this is not required, as Richard said. 7.5 milligrams is more than enough. And the NIOSH standard produces results that show that the respirator becomes unbreathable after some point. So it makes you realize, is this really applicable for the COVID framework or is it just for construction? Now, Conditioning and unconditioning, as Richard said, yes, you do get the individual odd lots that really shows differences. But if you actually average and you plot historical data and calculate the differences between conditioned and unconditioned for resistance and filtration efficiency, you don't see anything that, you don't see any pattern emerging apart from the odd lot, as you can see on the left-hand side of the diagrams. Finally, expired lots were tested, because it's also the assumption, if you have an expired lot, is it still effective? Is it 95? Is it an N95? In short, the answer is yes, it is still adequate and fit for purpose. So we have discussed with my colleagues, Richard and Joel, the response from NRC to the pandemic and the response of NRC when it comes to filtration, measurement and testing of respirators, how we've started from virtually nothing and haven't reached this point where we have built different systems within NRC. We've tested more than 4,000 respirators, and we're responsible for coordinating and disseminating the knowledge within Canada to continue the tests. And with this, I'd like to thank everybody at NRC and outside that have contributed. And I would like to thank you for your time. Thank you.
All right, thank you. We'll take about 5 minutes of questions and then we'll move to the next speaker. And if we have extra time at the end of the meeting and unanswered questions, we will try and answer them before we go offline. So the first question was from Terrence K. Clunan, which says, when you publish your data, are you stating that it was intentional to deviate from the existing NIOSH SDP 0059? And since there's deviation, will there be a separate PHAC published standard that is peer reviewed and cites the NIOSH standard? And Joel, did you want to answer that one?
I think Richard will answer that.
Richard, okay.
Well, there is a guide for respirator testing, and we're working on new standards for new Canadian standards for what this is going to be called PFE 95. And we're trying to make it so that it's as close as possible to the NIOSH standard, but this is meant, these deviations were meant specifically for qualifications of lots, particularly under an interim order. So there's specific just for the COVID response, and this was to address mostly the respirators coming in at the time. But there are standards being developed in Canada, and we're trying to align those with NIOSH as close as possible, so people don't have to accommodate more than one standard. That being said, we're considering whether to include this as a deviation in the long term for certification, and there's going to be CSA documents as well, or standards that are going to be developed in this regard. But right now there's a Health Canada guide that covers some of these deviations.
Okay, another question with regards to the loading. Did you actually do any comparisons with of different loadings for the filtration efficiency, either at the low loading you used, or did you do any higher loadings more like the NIOSH?
Can I answer that?
Sure thing.
So yes, we did a comparison test between 200 milligram loading tests and 7.5 milligram loading tests. And as I've mentioned in my presentation, when you do 200 milligram loading test, you actually end up reaching a point where you exceed the threshold specified by the standard, which is 245 Pascal for breathability, which means that after some point you continue load the mask, but the mask itself becomes unbreathable. So it brings it into the question, is this really applicable for the COVID framework? But in short, yes, we have performed tests for both.
All right, thank you. I think we'll have to move on to Margaret's part of the presentation. And as I said, if we have time at the end, we can return to some of these questions. Margaret, are you ready?
I will pull it up now. Give me 1 second. Okay, so I'm going to actually be taking this down a notch from being quite as technical as the last presentation. As Eva introduced earlier, I'm Margaret Sietsma. I'm at the University of Illinois at Chicago, and I'm an assistant professor there. And I'd really like to speak today about workplaces that decide for the first time maybe that they need a respiratory protection program and what that means in terms of how you would go about implementing that program, and then thinking about any sort of extra precautions or considerations that you need to take when thinking about how that works for coronavirus 19. So before we even start on that, I'd like to really emphasize that putting people in a respiratory protection program is not ever going to be an industrial hygienist's recommended first approach to protect workers from COVID-19. We still need to consider and think about following the hierarchy of controls that I've put a modified version of here. I've eliminated the substitution section, since while we all wish we could substitute COVID-19 for a less contagious or infectious disease, that's simply not an option. So I've just not included it in this hierarchy. So you need to really think through different ways that you can reduce your reliance on respiratory protection first and foremost. So just some quick examples. When you're thinking about ways to eliminate the virus, we've seen a lot of recommendations where we should tell people to work remotely, work from home as much as possible. And that just eliminates the chances of people coming in contact with each other and potentially spreading the virus. And then if you can't, you need to go to work, you can't eliminate it. You need to then think about implementing some sort of engineering control strategies as a first line of defense. And so some of the recommendations that we've seen throughout the virus have been to increase ventilation indoors, or to stay outdoors where there's lots of ventilation, or to add some sort of barriers around people who need to be at work, or around people, just to protect the people. Next, if those options are you've used up all of your elimination and engineering options, you want to move on to administrative control options. And so this might include altering work shifts to reduce just the number of people who are expected to be at work at any given time. Maybe moving into a 24-hour work schedule and having people work at different shifts to reduce how many people are present with each other at any given time. These are just some examples of elimination engineering and administrative controls, but there's obviously many other types of controls that you can implement before you get to the PPE section of the hierarchy. And for our purposes, I'm only going to be referring to implementing a respiratory protection program. So do you really need a respiratory protection program? And the guidelines vary slightly across different recommending organizations, but often we consider the disease to be most transmissible if you're less than 6 feet away from someone who has COVID-19 and you're in that space for greater than 15 minutes. In my opinion, if workers are required to work in close proximity for any sustained duration, they will probably be required to wear respiratory protection. Once you've decided your employees truly need to be in respirators in order for them to stay safe, you can't simply just give them a respirator and say, good luck. You really need to think very strategically about all of the elements included in a respiratory protection program. Whoopsie. Which I'll touch on here. So the remaining slides really focus on the requirements of the OSHA standard for respiratory protection, which is most applicable to employers and employees in the United States. However, I assume that the information presented here will be helpful in a variety of countries, but I cannot guarantee or confirm that all of these recommendations are applicable to all countries. So the OSHA 1910-134 is the respiratory protection standard. And here's just a list of all of the elements that need to be included once you've decided that you need to implement a respirator program for your workers. So you need a written program, you need a program administrator, you need to do a risk assessment, you need to provide employees information, you need to do some sort of medical evaluation to make sure that workers are able to wear respirators safely. You need to then do fit testing, come up with a plan to maintain and use the respirators, then train all your workers, and then think about how you will evaluate the program, keep track of all of your records, and then lastly, make sure that they're available. So if that doesn't convince you to try the hierarchy of controls and not put people in respiratory protection, then I don't know what would. So I'm going to walk through each of those things and then strategically think about any sort of coronavirus 19 things that you'll also want to consider. The first thing is a written program. So OSHA requires that you physically write down all of the policies and procedures for respirator use. So anything that I talk about from here on out needs to be written down as an official program. That's a log of what your institution is doing. The next thing you'll want to do is to assign a single person to assign a single person to oversee and implement the respiratory protection program. This person needs to have adequate training. So you can't just say, you know, Joe Schmo from down the road is going to be our program administrator. You need to document how they're trained or what makes them, you know, qualified to be the program administrator. An important note here is that this should never be an entire division. So I can't say that the Environmental Health and Safety Office is going to administer the respiratory protection program. It really has to be a specific person that needs to be involved. So some of the things that the program administrator needs to be doing is ensuring that all of the records are maintained, identifying who's going to be doing the fit testing, training, medical evaluation, ensuring that the risk assessment is conducted, ensuring the proper storage and maintenance of the respirators, and evaluating and updating the program as needed. So the program administrator doesn't have to be the person who does all those things. They just have to be the person who's in charge of the person who does all those things. And they're just the boss who, you know, is making sure that everything is running smoothly. And that's not to say that the program administrator can't be involved, but they don't have to be doing everything regarding the respiratory protection program. They can assign those duties out. The next and probably one of the most complicated aspects of this is conducting a risk assessment and selecting an appropriate respirator for your employees. Generally, when you're conducting a risk assessment in a workplace with maybe a chemical hazard, you need to know the concentration of the hazard in the workplace, and then you would compare that to the maximum allowable concentration. From there, you typically would need to identify an assigned protection factor, which will determine what type of respirator to put the employees in. Since we're talking about coronavirus, there's really no exposure limit or infectious dose, and there's pretty limited studies evaluating how to sample for viable COVID-19 in the air. So we're missing both of the variables we would need in order to do a proper risk assessment and respirator selection. In that case, we just have to use best practice and judgments. And the literature suggests that an N95 filter is sufficiently able to lower any exposure that anyone may have. So employees exposed to COVID-19 at work should use, at a minimum, a respirator with an N95 filter. N95 filters are capable of filtering out at least 95% of the 0.3 micron particles, and it's more than likely that they're able to filter out greater than 95% of particles in all other size ranges. We know that viruses travel and transmit via aerosol particles. And so that's how the N95 is capable of protecting the workers. And oftentimes we're not really concerned about the smallest, the size of the coronavirus viron itself, because it's not traveling by itself. It's traveling always on some sort of infectious disease particle. So then the next thing you're going to want to think about is the certification. So you want to make sure that any respirator you choose has appropriate certification. We've seen a lot of instances over the summer of maybe some fraudulent N95s being produced, or people claiming that they're selling an N95 without any sort of certification. So this list here is designations from around the world that all provide similar filtration capacity to an N95 respirator. An N95 respirator for use in the US needs to be NIOSH certified. If it is NIOSH certified, it will have most, if not all, of the markings shown here in this figure, and it will appear in the NIOSH certified equipment list, which I've provided a link to. I'm not as familiar with other country certification lists, but you should always ensure that the respirator you are placing your workers in has been properly certified. And that goes to the previous conversation that we just had. So in the US, NIOSH you would typically find a TC number, which is the approval number on the face of the respirator. You would also maybe find the model, the lot number, the filter designation for making sure that it's at least an N95 filter. NIOSH will be written probably somewhere on the respirator. So those are just some of the markings that you would look for to make sure that it's been appropriately certified. Lastly, you want to, in your risk assessment and respirator selection, you want to think about, now you've decided on the filter, but you haven't decided on the type of respirator. In most industries, a half mask respirator is probably sufficient for protecting against COVID-19. Two examples of a half mask respirator include a disposable filtering facepiece respirator, as shown on the left, or an elastomeric respirator, as shown on the right. Either respirator can be purchased with an N95 filter media. In the filtering facepiece respirator, the filter is the entire facepiece, whereas in the elastomeric respirator, the filter is a separate cartridge, shown here in purple, that can be changed out as needed. In some industries, the worker may require face or eye coverage. In addition to those cases, the worker should wear a full facepiece respirator or add something like a face shield or eye protection to the personal protective equipment ensemble. When adding additional items to the ensemble, though, then you have to think about how does that interfere or conflict with the respirator to perform. So for instance, if you were to add some sort of goggles, they might interfere with where the respirator is on the face, and that might affect how well it's protecting the wearer. And or maybe if you have something that has a hood overhand, then maybe it might affect where the straps are. So then we've received a lot of questions over the summer, and I've been involved in a lot of conversations regarding what about exhalation valves? So an exhalation valve makes breathing out of the respirator much easier. It's a one-way valve, so instead of air going through the filter to be exhaled, it just goes through the exhalation valve directly. These exhalation valves are very common on elastomeric half mask respirators, but they can also be found on some varieties of filtering facepiece respirators. As I'm sure everyone at this point is acutely aware, there's mask guidance almost everywhere, which requires people to wear a mask as a method for source control, or how to reduce how many particles you spread into the air when you exhale. Because respirators are designed to protect the wearer, if a respirator has an exhalation valve, the exhaled breath has a simpler path out of the respirator without needing to go through any filter media. This means that the respirator with exhalation valves may or may not be very useful as a source control measure. I'm not going to really get into a lot of this, but just to say that exhalation valve research is ongoing, and there's a lot that we don't yet know about how many particles come through them. But when you are designing your respiratory protection program, I would strongly advocate thinking about what happens with the exhalation valve and how you will consider that in terms of source control issues. The next thing that everyone needs to do is that employees need to be medically cleared in order to be able to safely wear a respirator. This needs to be done by a physician or any sort of other licensed healthcare professional, and it should be done at a time that is convenient and at no cost to the employee. And this just simply makes sure that when you put someone in a respiratory protection program, that you're not causing extra harm to them by forcing them to breathe through a respirator instead of without a respirator. The certification process for a respirator primarily tests the filtration capability of the filter material. And so we saw that was the entire first presentation, thinking about, does the filter material provide adequate filtration? But in order to fully protect the worker, a fit test must also be conducted. The fit test shows how well the respirator seals to the wearer's face. And this seal is imperative, as air is always going to choose the path of least resistance in and out of the breathing zone. So if the respirator does not seal completely around the face, the air will simply go through gaps of the respirator and the wearer's face. There are a variety of methods for testing the fit of a respirator, and they are laid out in Appendix A of the OSHA Respiratory Protection Standard. Most commonly, we use a qualitative or a quantitative fit test. These are shown here in this picture. Each time you change the respirator make or model, the employee will need a new respirator fit test. Because of this, it will be easiest for you if you choose one make and model of respirators and purchase that make or model in bulk. Now, given coronavirus 19, that purchasing any sort of respirator in bulk can be very difficult. So we'll talk about that in a little while. But you will need to do a new fit test on every type of respirator each time you run out of a certain make or model. In order to conduct quantitative fit testing, we often have to poke a hole or probe the respirator. If a hole is poked through the filter media of the respirator, then that respirator has to be thrown out because it no longer is able to provide respiratory protection. So CDC currently is recommending that qualitative fit testing be done for COVID-19 in an effort to conserve supply. This would allow the respirator to be used again in the workplace. For elastomeric reusable respirators, you can choose to do qualitative or quantitative fit testing because an adapter can be purchased to quantitatively fit test an elastomeric respirator without puncturing a hole in it. That makes it feasible. The last thing you want to consider when thinking about the fit test is this graphic that went viral, I think, earlier in the summer. So in order to ensure that a respirator fits really well, all employees must be clean shaven in order to get that good seal between the respirator and the face. This chart describes a series of common facial hairstyles and whether or not they would be acceptable with a respirator. The short answer is if facial hair interferes with the seal of the respirator, then it's generally allowed, and that's just a rule of thumb. So because of this issue, anyone who's implementing a respiratory protection program for the first time will realize pretty quickly that it's helpful to keep a shaving kit handy near where people are going to be using their respirators in case an employee shows up one day and has forgotten to shave before they come to work. So then comes maybe one of the more challenging things, once you've gotten through the risk assessment and the fit testing, is thinking about how you're going to maintain and use the respirators. In short, you need to consider how to store, care, and maintain the respirator, and you need to consider any conditions of reuse on the respirators in this section. So thinking about maintenance and use during coronavirus, you want to think about strategies for extended use or reuse. So if you're considering telling employees that they need to reuse the respirators and you're giving them elastomeric respirators, you then need to consider how you can disinfect and how they will be disinfected and reused and circulated throughout the facility. If you're considering filtering face piece respirators, the general recommendation is that they should not be taken on and off more than 4 times in a shift, and that a new one should be used at the start of each day. Each time a respirator is reused, it should be inspected to ensure that all parts are adequately working. This might involve, if you're using an elastomeric respirator, thinking about all of the one-way valves, make sure that they're adequate and working. And for all respirators, looking at the straps, making sure that they're still maintaining their elasticity. And then lastly, just making sure that there are no holes or any punctures that have been introduced into it since it was last worn. You can also use something called a burn rate calculator just to ensure how fast you're going through respirators and making sure that you are planning enough in advance to ensure adequate supply of respirators. These are just a few of the considerations for COVID-19. As you start to plan out exactly how you will implement a respiratory protection program, you will soon come up with more and more things that need to be considered. Just this morning, we were considering if you do a quantitative fit test, how often do you change out the tubing for that, you know, in order to make sure that employees are not being exposed. So it just kind of trickles down into more and more questions. When you train your workers on how to use respirators, you need to train them on all elements of the respiratory protection program. Training should not focus solely on how to correctly doff the respirator or how it is fit tested, but really needs to encompass why the worker needs the respirator, how to inspect it, what to do if there were a malfunction, who do they go to if they have any problems, where can they find records of their medical evaluations and fit testing, where does the facility store extra respirators or extra pieces for the respirators. And so the workers really need to know and understand all elements of the respiratory protection program in order for them to be best protected. Either periodically throughout or at the end of the training, there should be some sort of mechanism to assess how well the employees understood the training. So you need some sort of test or quiz. Due to coronavirus, online modules are probably being best implemented at this point. Although normally I would suggest in-person training is better than online modules, as people tend to just click through online trainings. So one of the last things that you need to consider is in your program evaluation, you need to think about how you will evaluate this respiratory protection program to make sure that it's working out in the way that you expected it to. So one of the ways that you can do that is to solicit feedback from employees as well as the administrators. So this program evaluation should happen on some sort of regular basis, and it shouldn't just be a team of 3 people sitting in a room saying, yep, it looks like it's working great, we have had no problems. You really need to ask the employees, like, what are the problems they're facing on the floor? In addition, you might want to consider including observations of how employees are actually using the respirators on the floor, as well as reviewing of any records. Speaking of records, they need to be centrally located and accessible. They need to contain all of the results from the risk assessment, describing how you came to the choice of respirator that you've come to. You need to think about, you need to include all of the results from the fit testing as well as the medical evaluation. And then availability. So this is a big issue right now, and you need to, if you're going to put people in respirators and tell them that they need to be in respirators, you need to think about making sure that there's an adequate supply of respirators. And right now, I know every time I need to order respirators for any sort of study, they're back ordered. And so you need to just make sure you have a process in place and you're planning enough in advance to make sure that you're providing workers respirators when needed. This is where some of those extended use and reuse policies may be applicable or may need to be relied on if needed. So once you've done all of these things, then only then can you safely tell people, you can give your worker a respirator and say, good luck and hope you've done all right. But it's not an easy process, and it needs to be really carefully thought out. And so that is all I have for you.
All right, thank you, Margaret. So we do have a few questions here. One of the questions involved thoughts on using powered air purifying respirators as a form of protection in the workplace for this application.
Yeah, I think that powered air purifying respirators are a great option as well. I'm sorry I left them out. If it is a tight fitting powered air purifying respirator, it also might need to be fit tested. So that is also a consideration. But, I think that again, you might want to just think about source control issues if there are exhalation valves.
And a couple of individuals have pointed out that masks with exhalation valves can be covered by cloth masks for source control or surgical masks. That's not necessarily as easy with a PAPR. There was a question about where does the not removed more than 4 times per shift guidance come from?
I could pull it up, but I think that there was a paper done at maybe by NIOSH that looked at multiple donnings of respirators and how that affected respirator fit. And I believe that that recommendation, which is what is on CDC's website today, I believe that's where that recommendation came from. But if anyone is interested, I can try and find that paper. But it was just that, I think that the recommendation came from after multiple donnings, respirator fit started to drop.
Okay, and another question sort of going to the other end of the spectrum. In a service sector workplace, if everyone is wearing some form of face covering, is that sufficient as opposed to N95 respirators?
So the question is, if everybody is wearing some sort of face covering as a source control measure, is that sufficient instead of putting people into respiratory protection? I don't know that we know. I know that we know that the face coverings can reduce sources, emission of sources by some capacity. I don't know that we know how well how exactly what that number is or how well they are able to reduce the source emissions. Specifically thinking about smaller or different sized particles that may go through those source control options. So I always like to remind people that face coverings are not a substitute for social distancing and really maintaining our distance, because if you are to reduce how many particles you're exhaling, let's say by half, which would be a pretty high number, that still doesn't mean that you can stand and talk to someone or be in close proximity to someone for an indefinite amount of time, because you're still emitting some particles, right? So I think that you're just walking a fine line there. And if you are asking people to be in proximity to everybody, to many other people on a long period of time indoors, then you really need to be thinking about where respirators fall in protecting those workers.
And in terms of the reuse and sterilization, question, as the virus is supposed to denature quickly at 70 degrees Celsius, can dry heat overnight be used to sterilize them for reuse?
I am sorry, I'm not an expert. I'm on the current disinfection guidance right now for reusing respirators. We know that once a particle is trapped in filter media, that it will tend to stay there. So you're thinking mostly about any sort of particles that are on the outside of the respirator. And I would refer to the, guidance from governing facilities on how to best disinfect a respirator. I can find those guidance documents for you if requested.
All right, thank you. I think that covers most of the questions. I would just like to offer something first as a sort of an overall answer to several of the questions regarding where information can be found. On the ISRP website, there's actually a lot of links to relevant information with regards to different national guidance documents and positions. So I would recommend that not all of the papers that might support the studies, but considerable information on what various national standards are or recommendations are on the ISRP website, both in the standards section and in our general news section when things are updated. So I would recommend looking there, and of course becoming a member, in which case you have access to all of our internal resources as well. So I think we do have time to return to some of the questions from the first presentation. So let me just return to those. One question that was asked, which had to do with the effect of loading on the performance. The question was actually related to the effect of loading on the filtration performance and not on the breathing resistance, which was the question that was answered. So did the loading actually have any effect on the filtration performance?
Yeah, I think I tried to answer that again in the work. I think if I understand what they're asking, if we compare the initial filtration measurements to longer measurements of loading, so we can measure the filtration over that 7.5 milligram loading, and we can also continue to measure over the 200 milligram loading. Would there be an impact in going higher on the filtration efficiency? And there is, from what we've seen, there is some variation in that filtration efficiency over the first little while. Typically what we think what happens for good respirators is that the charging mechanism, the filtering mechanism through charge, that attracts the particles initially. And as those charge sites become blocked, then the filtration efficiency goes down a little bit. But at the same time, as the mask gets more loaded, its mechanical filtration becomes a little bit better. So you have sort of one mechanism is decreasing and one mechanism is increasing. You can see that in one of the slides that Triantafillos put together, is that we can see a little bit of a dip over the first, 10 or 20 milligrams, and then it comes back up over time. We can't say that that's typical for every respirator. For ones that we've tested, that seems to be the case, that you might have a little bit of a variation of 2 to 3%. But we wouldn't expect to have a huge difference. That being said, we haven't tested all the potential materials, so we don't exactly know how that would occur. But the reason why we looked at why 7.5 milligrams, that's only for a particular use. That's just for the COVID response. If we wanted to go to use this in sort of industrial settings where we can have that higher loading, then it would be necessary to test to that higher loading. But just for the COVID response, we think we can, as long as the filtration efficiency doesn't fall below 95% over that 7.5 milligram range, then we think we'll be okay. And it's sufficiently protective for healthcare workers.
All right, thank you. Okay, I'm going to ask one back to Margaret again. Given the near universal risk of exposure to COVID, do existing respiratory protection programs need to be expanded to cover all workers, and how does OSHA address this?
I would like to remind people that we should be considering all sorts of other control measures before we consider expanding to all workers everywhere. I think that there are a variety of control strategies that we can think through pretty in a lot more detail before relying on respirators. So I do not believe that all workers need to be covered in a respiratory protection program. OSHA does have some guidance documents out about how to think about expanding your respiratory protection program, and you know how to think about fit testing and training people in a rapid basis. But I would strongly urge people to think about the rest of the hierarchy before relying on respiratory protection to protect all their workers.
All right, thank you. There have been a lot of questions posed regarding elastomeric respirators. I think it would be helpful if the NRC team could just answer how their work relates to elastomeric respirators with similar filtration media.
Sure, I'd like to answer that. So what we've been testing N95 masks and KN95 masks from manufacturers, but we've also been testing filtration media from manufacturers, especially in Canada. So that means we're testing the materials which go into respirators. And so that material a given material can in principle go into an elastomeric respirator or into another respirator. So we don't focus on that in our work, but we are supporting work in that direction.
Yeah, I can also add that we've done lots of testing on the elastomeric face pieces themselves. This is something, I think we're testing a lot more of that now, actually, probably that might make up maybe 25 to 30% of what we're testing now, if not more. So this is something that's certainly something that's becoming interesting to product development, and it may be taken up by healthcare communities. Well, I think the only concern that people have with that is how do you ensure that the face piece itself is clean even after you take out the filter pieces. And so looking at sterilization techniques, I think people are looking at for these elastomeric systems. But from a ecological standpoint, and even some cases a comfort standpoint and a fit standpoint, those are certainly something interesting. Thanks.
All right, and we have time for one last question, I think, before we close out. There was a question about the SARS-CoV-2 particle size and how that fits in with the particle size distributions that you're using for testing.
Yeah, so the SARS-CoV-2 virus itself is about 100 nanometers in size, and that's the size of the particles that we use. But what's extremely important is that when that particle is emitted from a person, it's emitted from the lungs in the context of other lipids, proteins, and other biological material. So the question is, what particles are infecting people rather than what is the size of the virus, because the virus comes packaged with all this other stuff. And we don't know the answer to that. And that's why we do our tests under the most difficult conditions of the smallest particles.
All right, thank you very much. All right, I would like to thank all of our speakers very much for some engaging presentations that obviously got lots of interest from the webinar attendees. And so thank you for being with us. We really appreciate it. Thank you to all the attendees for joining us for this webinar. And if I could remind you all again, as I said, there is a lot of information on the ISRP website. If you have any unresolved questions coming out of this webinar, you can ask us. You can ask me, president@isrp.com. And we'll try and pass them along. And we'd encourage you to attend our next session on the European response to COVID-19. And thank you all.